The example hand calculations for lab 3. So for lab 3, you're going to be designing an inverter, a NAND, and a NOR gate. And the hand analysis for this is just doing the inverter hand analysis, and it has to do with sizing the pmos width. The pmos width controls the delay from low to high, and you want that to match with the delay from high to low so that you have a symmetrical inverter. So we know from the last couple homeworks that TPLH equals alpha P over Kn prime W over L. Excuse me, this is HL, not LH. And VDD. And TPLH is equal to alpha, this is an N, alpha P over Kp prime W over L P VDD. So for the sake of hand calculations, we can assume that alpha N is approximately equal to alpha P. That's a fine assumption to make. They're usually pretty close. They're off a little bit just because the thresholds are off, but they're very close. The VDD is obviously the same. So now all we have left are these two terms. So we're going to want to set Kn prime over W over L times W over L equal to Kp prime W over LP. Now, we're told that the L's for both equal each other. So what we're left with is Kn prime Wn equals Kp prime Wp. And so Wp equals the ratio of Kn prime over Kp prime times Wn. And we have Kp prime equals 95.75, and we have Kn prime equals 274.75. These are both in microamps per volt squared. And we have Wn equals 0.45 micrometers, or 450 nanometers. That gives us a Wp of 1.29 micrometers. Now we want to find out what our TPHL and TPLH are. And so we don't really want to do it using this method. We want to do it using a new method that's shown in the book on page 1132. This new method is empirical based, so it's using numbers from experiments to get values. Essentially, what you're saying is you're treating the MOSFET as a resistor, and then you're saying TPHL equals 0.69 Rn times C. So this is just the standard form. RC here is tau, 0.69 tau is TPHL. So we have to find what Rn is. And it's the same thing for TPLH, with Rn being Rp. So TPLH was 0.69 Rpc. We know C to be, CL is 1 picofarad. So the formulas given in the book are Rn equals 12.5 kilo ohms over W over L, and Rp equals 30 kilo ohms over W over L P. So we get Rn equals 8.33 kilo ohms RP equals 6.98 kilo ohms. And that gives us a TPHL. It's equal to 5.75 nanoseconds, and a TPLH equal to 4.81 nanoseconds. So these are going to be a little bit off because we use different equations to calculate TPHL and TPLH than we did to calculate what equal delay would be. That's just because these are just general empirical formulas. They get you really close to the correct value, but they're not as accurate as doing these. But for hand calculations in a starting point and knowing about where your delay will be, these are very accurate. But overall, if you want to match delays, you can just use this for an inverter. And I'm sure you'll go over that in class some more, matching delays. It's very important. But so these are our TPHL values and TPLH values. And so in your lab, you're gonna code up the inverter in cadance, and then you're going to sweep through different values of WP. So you're gonna have WP be like a range from like say 0.5 to 3.5 micrometers. So you're going to have a range here, and that's going to iterate each time, and you're going to graph the rise time, the fall time, TPHL, and TPLH. And so you're going to get something that looks like this. You're going to get a line that looks like this, a line that looks like this, and you're going to get something that looks like this, and something that looks like this. So this is WP down here, and this is going to be time in nanoseconds over here. So this right here is your rise time, and this right here is your TPLH. And so and then this is going to be your fall time, and this is going to be your TPHL. And so you'll notice that the only things that are changing with WP are rise time and TPLH, because those are the two that are affected by the pmos. The two that are affected by the nmos don't change. So then you're going to find this point where the TPLH and the TPHL intersect, and that's the WP where the delay is equal. This point where the rise time and fall time intersect is going to be a slightly different WP, and that's where the rise time and fall time are equal. Usually having the delay equal is more important than having the rise time and fall time equal, but you need to know what the different values are. So you're going to do this for the inverter, and then you're going to compare that to your hand calculations. You're also going to have to do a transient, but that's just doing standard stuff. And you're going to find that you're going to get pretty close. The WP is within like 4%. That's pretty good. The delays are inside like 30%, and like I said, that's just because these empirical formulas are off a little bit, but they're still pretty close to the actual numbers. And then you're going to do this same delay for the NAND and the NOR, but you don't have to do the hand calculations for that. So you do these delays for each of the inputs, changing the WP, and you calculate out what the WP needs to be to have equal delay time. That's all it is. It's just getting to know cadence, getting to make these building blocks and understanding how to tune them so that they're optimal. You want the delays to be perfectly symmetrical and that's the optimal point.